Today, we are going to be talking about air pressure and wind and how these two things control a huge part of our everyday weather. Let's start with air pressure. So, air pressure is the pressure exerted by the weight of the air above you. Even though we don't necessarily feel it, the atmosphere is actually incredibly heavy. At sea level, all of that air pressing down on us adds up to 1 atmosphere, or 14.7 pounds per square inch, or 1013.25 millibars, or 29.92 inches of mercury. Now, you don't need to necessarily memorize all of those, but you should recognize that they're all just different ways of describing the exact same thing, the amount of air pressing down at you and at sea level. So how do we measure air pressure? Well, we use something called a barometer, and there are two main types. So let's start with the mercury barometer. Imagine a bowl filled with mercury and an inverted tube sitting inside of it, also filled with mercury. The air pressure pushing on the mercury in the bowl forces the mercury up into the tube. So when the air pressure is increasing, the mercury rises, and when the air pressure decreases, the mercury falls. This method is still one of the most accurate and reliable ways to measure air pressure. Even with the toxicity of mercury, we still rely on this today. The second type of barometer is an aneroid barometer. You might have seen these before. They're a circular dial with labels like stormy, rain, change, fair, and dry. They are more practical, but they can be a little temperamental because they don't always perfectly match the weather that is happening outside. That being said, there are some useful applications to aneroid barometers. First, they can be connected to bar graphs, and those barographs can record pressure changes over time. Aneroid barometers are also used in altimeters, so measuring the air pressure in airplanes, or for people that go hiking, or map making, so getting that elevation. Personally, when I'm hiking or looking at terrain maps, I find this to be really useful in understanding the elevation changes, especially when hiking in the mountains where the air is changing and the air pressure is less. It's helpful to have that knowledge of what the air pressure is actually doing. And also when storms are coming in, knowing when to seek shelter versus when it's okay to just pitch a tent. Now let's connect air pressure to weather. So we have two main types of pressure systems: low pressure systems, which result in something called cyclones, and high pressure systems, which result in something called anticyclones. In a low pressure system, the air is converging and rising. On the other hand, in a high pressure system, the opposite thing happens. The air is sinking and diverging. In a low pressure system, rising air leads to cloud formation, wind, and storms. In Minnesota, we see this a lot during April and November as the seasons are changing. In April, we have warmer temperatures that are colliding with the colder temperatures, and we get wind and rain. In November, we have cooling temperatures as the colder air starts to dominate, and then we still get storms, but this time it's snow. Personally, I noticed this change in weather as the warm, moist air from the southeast collides with the cold, dry air of the northwest, and that clash creates this instability in the atmosphere, And that is when we start to get some of our most interesting storms in Minnesota. High pressure systems lead to clear skies and calm conditions. If you think about Minnesota winters, especially December through the beginning of February, they are cold, they're dry, the skies are clear, but they're incredibly cold. This is a classic high pressure system that is dominated by Arctic air from Canada. Another really cool feature, specifically here in southwest Minnesota, is something called Buffalo Ridge. Buffalo Ridge rises about 1,000 feet above the surrounding prairie in southwest Minnesota. And so as the prevailing northwest winds move downhill, they speed up. And so southwest Minnesota tends to be much windier than the rest of the state. And we harness that wind, as is evident by all of the turbines and windmills that are in the southwest part of the state. So what is wind anyway? I mentioned earlier something called prevailing winds. So let's define what wind is. It is the horizontal movement of air. We measure wind using two instruments, a wind vane and an anemometer. The wind vane tells us the direction the wind is blowing, and the anemometer tells us the speed that it's traveling. So you can think of a wind vane like a little rooster on top of a barn, and it has an arrow and it's pointing the direction that the wind is coming from. An anemometer, on the other hand, sometimes you see these at the tops of like aircraft carriers and they're spinning around next to all of the radar and all of that other equipment. But an anemometer, it has two little cups on it and it spins as the wind is blowing, and then that spinning is connected to gears that tells us how fast the wind is moving. So what causes the wind? There are three main factors that control the wind: pressure gradient force, Coriolis effect, and friction with the earth. We're going to start with pressure gradient force. Air naturally will move from a high pressure situation to a low pressure situation. That movement is what creates wind. So the bigger the difference in the pressure, the stronger the wind. So why do these high and low pressure systems exist? Well, it starts with uneven heating of the earth. At the equator, the sun is shining down on the equator all the time, and we have warm air. Warm air rises, which creates this low pressure system. Now, as the warm air circulates up to the poles where it's colder, that air sinks, creating a high pressure system. If Earth didn't spin, the air would simply move up from the equator. We'd have a band of low pressure systems at the equator. It would travel up to the poles where it would cool and then sink back down, and we'd have a high pressure system at the pole. But the Earth does spin, and that is what changes our weather and our wind patterns. The Coriolis effect is what happens when the Earth is spinning and the air is getting deflected. So the air deflects to the right in the northern hemisphere and the left in the southern hemisphere. And the example that I like to think of, if you were trying to fly straight south from the North Pole to Tallahassee, Florida, you'd actually end up closer to New Orleans because the Earth is rotating under you while you're traveling due south. The same deflection happens with wind patterns all over the planet. Now let's scale this up globally. At the equator, we have that low pressure system where the warm air is rising. It is trying to rise up to the poles, but remember how the air pressure gradient slows down with distance? Well, it starts to sink at about 30 degrees latitude. So that sinking air creates a high pressure system at 30 degrees latitude. We call those the horse latitudes. And that high pressure system creates warm, dry air, and that is where we find most of the world's deserts. Between the equator and the horse latitudes, the winds move and are deflected, and we call those the trade winds. And they move from the northeast in the northern hemisphere, and they move from the southeast in the southern hemisphere. That high pressure system at about 30 degrees latitude is also pushing air north and south. That north and south push of air we call the westerlies, which is still warm air, but it is being deflected in the opposite direction as the trade winds. Now, at the pole, we already talked about this high pressure system where air is sinking. That produces wind going away from the poles. We call those the polar easterlies. Now, when those polar easterlies collide with those warm westerlies at about 60 degrees latitude, we get what is called the polar front. And it's a band of stormy, snowy, cloudy weather where those two wind systems collide. So this entire wind system and the Coriolis effect and even the pressure gradient explains why certain regions on the planet are rainy or dry or stormy or stable. So for example, we have a ton of rainforest near the equator where we have that low pressure system. We have rising air that's creating clouds and creating rain. And then that air is sinking at 30 degrees where we have all of the world's biggest deserts. So a lot of these large wind systems that I explained, the pressure gradient force and the Coriolis effect, are more applicable to our global climate and overall trends in the weather. However, closer to the ground, the wind experiences friction as it's passing over the earth. This is where we get some local wind systems. During the day, land heats faster than the nearby ocean or sea or lake. And so as the land is heating, the air rises and it starts to circulate over to the cooler water or the ocean. And as it brings that back into the land, we get a cool air that is blowing in from the sea. We call that a sea breeze. At night, the land is actually cooling faster, and so the air is sinking near the land and that wind blows out from the land to the sea where it rises over the sea. And so that creates what we call a land breeze. And that's a warm land breeze going out to sea. Mountains are another location where we have localized wind patterns. So during the day, the tops of the mountains are getting warm and there's warm air rising along the mountain slopes. And that warm air rising creates a kind of a current of wind that's blowing up the mountain sides. That's called a valley breeze. And then in the middle, it sinks down into the valley again and creates this kind of circular pattern. At night, the mountain slopes, they cool really quickly thanks to the high altitudes, and it reverses that breeze. And so at night, there's a cool breeze that is sinking down the sides of the mountain and then it rises from the middle of the valley. Finally, when we have large mountain ranges, similar to the Northern Rockies, the air will descend down the side of the mountain range, and as it compresses, it warms up. Remember, this is something we call adiabatic warming, and those warm, dry winds are called the Chinooks. And those happen in places like Wyoming and Montana, where we have what is coined a high desert. It's very warm, very dry, and it's thanks to this high pressure system that sits over the Rocky Mountains and blows these warm, dry airs down the side of the mountain. The other cool piece of that high pressure system in the Rockies is the other side of that swooping air goes down into Southern California and crosses down into LA and San Diego, and they have something called the Santa Anas, and that creates warm, dry air in Southern California in that Mediterranean climate that we all love. So to kind of wrap up all of this information, air pressure differences is what creates wind. The Earth's rotation is what changes the wind direction. And we have these global patterns of wind that shape our climate. And then we have little nuances in our local geography that fine tunes what we actually experience when it comes to weather. So, whether it's a calm winter day or a powerful spring storm, it kind of all comes back to how the air moves through the atmosphere. Hope you have a great rest of your day, whatever the weather may bring.